Welcome to lesson 30 of industrial instrumentation. In this particular lessons, we will cover Synchro, which is basically inductive based devices, and this can be used as an error detector or position sensors, not the linear position. Rotary positions can be rotary position can be detected, can be measured, and we will get the voltage outputs. As well as Synchro is widely used for the feedback control systems in AC position control systems. And also in continuations with the Synchro, we will consider the micro Synchro, or which is called more popularly named as micro scene. That is also will be covered in this particular lesson. Synchro is actually still now you will find it is used, though there are digital shaft encoders which is used for knowing the position of the system, positions of a rotary shaft, but the Synchro along with the servo mechanisms, where that means with the two phase servo motors, can be used for position control system. That means I will give some particular position that can be easily attained by the use of Synchro when the Synchro is used as a error detector, as well as for remote transmissions of the signals. I mean Synchro is also can be used over a long distance. Synchro can be used. So, let us look at the contents of this particular lesson. Lesson 30 Synchro. Contents are the Synchro always you know that it has a transmitter and it has a receiver. So, we will consider the transmitter first as well as receiver. The two are almost same thing. I mean it has one rotors and a stator, both in the case of transmitter, and the receiver we do not call it, we call it control transformer in the case of Synchro. So, it is always is to be used in the pair form. That means, transmitter cannot be used alone or receiver cannot be used alone, which is called as a control transformer. So, this always is to be used in pair. So, that is the reason sometimes we call it always, sometimes we call it Synchro pair instead of calling just Synchro, because Synchro alone one transmitter or one receiver will not work, right. So, keeping that in mind, so always please note that the Synchro always is used, whether it is error detector systems or AC position control systems or as a mechanical shaft error measurements. I mean all these things I mean involved with a Synchro pair, that is one transmitter and one control transformer. So, we will discuss these details, this transmitter and control transformer. The first we will discuss the transmitter, then we have control transformer, which is nothing but a receiver, but we are calling it control transformer because there is a transformer action. The transformer action is also there in both in the transmitter and the control transformer, but we are calling it control transformer. Then we will discuss the Synchro error detector. Synchro can be used as error detector because there is a misalignments of the two shaft can be detected, because we will get a proportional output voltage from the misalignment of the shaft. That can be utilized to use any control systems. We will also discuss a micro scene or micro Synchro, which is a smaller versions of the Synchro with it is also a Synchro. That means, it can be also used as a position sensor, but the advantage of the micro scene is that it is a basically used for a low torque devices, and you will get the there is no winding on the rotor of the micro scene, whereas in the case of Synchro we have windings, that means coil windings both in the case of rotor as well as in the stator, because since it is a motor devices it must have some stator and it has a rotor also, and stator and rotor. Okay. At the end of this lesson, the viewer will know the principle of operation of a Synchro, the construction of rotor of Synchro transmitter, the construction of rotor of Synchro control transformer, AC position control systems. We will see that AC position control systems can be used, that we will discuss in details here. Introduction, let us look at Synchro is an AC electromechanical system which basically makes the angle measurements. Okay. Angular measurements of the shaft can be detected. That is a rotary sensor. It is not actually for the linear measurement, but it is a angle measurement devices, right. Just slightly different. I mean, so far in all the 20 lessons we have not discussed anything on the angle measurements. Now, with the rotary angles measurements is possible. That means, if there is a misalignment of the shaft, that can be used, I mean that can be detected by the help of Synchro. Synchros for angle measurements are most widely used as components of servo mechanism. Servo mechanism is nothing but a feedback systems, okay, automatic feedback control or automatic control systems. In short form, we call it servo mechanism, where they are used to measure the and compare the actual rotational position of a load with its commanded position. Okay. Why there will be some difference? Because we have some desired position of the load, rotary position, angle position, that can be achieved with the help of synchro and in conjunction with the servo mechanism if the torque is large, right. Otherwise, we can use a synchro pair. We will discuss all this in details. To perform this operation, a synchro pair is used and they are called a transmitter and a control transformer. Okay. Construction is almost same, stator construction is almost same, only the rotor constructions are different. We will look at. The pair is used to detect shaft position error. Okay. Synchro pair, as I told you, sometimes we are just calling it pair, is used to detect the shaft position error. Theory. Synchro is a rotating device that operates on the same principles as a transformer and produces a set of voltages correlated to the angular position. Okay. There are 3 stators. So, from each stator, okay, across the each 2 stators, that means if you have a 3 stators between the stator 1 and stator 2, stator 2, stator 3, stator 3 and stator 1, we will get some voltages that can be calibrated in terms of the position of the rotor, right. So, as the rotor position changes, the voltage output also will change. This is a diagram of a schematic diagram of a synchro transmitters, because it is in it is a big diagrams, we cannot accommodate it in a single slide. So, in the it is spreaded over in the 2. So, you see this is a single phase excitations we are giving here, this is a rotor. So, this is the rotor, okay. This is the rotor and this single phase excitation goes to the rotor through a slip rings. Obviously, we need slip rings because rotor will rotate. Obviously, we do not need any slip rings in the stator. So, we will get some voltages across the stator, that means between S2 and neutral and between S3 and neutral as well as between S1 and neutral, right. We will get a voltage. Let us look at the second slide. You see here, this is a complete schematic diagram of the synchro transmitter, that is a just diagram, this is a complete diagram of the synchro transmitter. Let us look at. Here I am giving between R dash and R double dash, since it is rotor. So, I am giving the name R dash and R double dash through slip rings and to the rotors of the synchro. Okay. We have 3 windings in the stator, which is this complete systems we call it the transmitter. This is the rotor of the transmitter. Okay. It is a slightly different, if you can look at it, is a dumbbell shaped. We will discuss all these details why it is dumbbell shaped, because actually the command will give to the this rotor. So, it should not load actually the system in which we are connecting this shaft, whereas the control transformer rotor will is typical cylindrical shape, okay, that we will see later on. Synchro transmitter, let us look at. Stator is a Y connected stator similar to a 3-phase induction motor. Okay, though it looks like a 3-phase induction motor, but we will see that we will get a single phase output at the stators of the synchro transmitter. The rotor is salient pole, dumbbell shaped. Okay, why? To reduce the weight of the rotor, because if the is a mechanical loading will not be there if the weight of the rotor is less, with a single winding. We have a single winding on the rotor of the synchro where the excitation, single phase excitation is going through slip rings. Let the voltage applied to the rotor of a synchro transmitter be ETR, okay, time domain, ETR, okay, this is the magnitude of the signal, sinusoidal signal into sin omega t. Okay, this is the omega is the excitation frequency of circular frequency of excitations of a single phase excitations, which we are giving to the synchro rotor. Clear? When the rotor is in position as shown in figure, okay, let us go to the figure. This is the rotor position when the rotor is aligned with S2, okay, if the position is something like that. When the rotor is in position shown in figure 1, which is defined as electric 0, the voltage induced across the stator winding between S2 and the neutral N is maximum. Okay. In this particular position, rotor and the output voltage will be maximum. The induced voltage across the stator windings between S2 and the neutral is N is maximum, okay, and is written as, this is the neutral, neutral we are abbreviated as S. Please note, this is the neutral, we are abbreviated as S. That means this is the neutral, we will abbreviated it as N, and is written as ES2N between the stator winding 2 and the neutral is K, the factors we are introducing into ETR sin omega t, no phase shift, nothing, where K is the constant of proportionality and two other stator voltages can be written. Now, these are the constant of proportionality and the two other stator voltage. There are two other stator voltage between the stator 1 and neutral and stator at the 3 and neutral. So, those voltages will look like, you see, ES1N K ETR cos 240 degree into sin omega t and minus 0.5 into K ETR into sin omega t. This is our ES3N time domain t K into ETR cos 120 degree into sin omega t equal to minus 0.5 K ETR, because 120 degree will be K ETR. ETR is because it is in transmitters, we are giving it ETR subscript TR. So, I have abbreviated these transmitters by TR, right, into sin omega t. Therefore, the voltage across the stator windings are ES1 S2, that means instead of neutral, if I measure the voltage across S1 and S2, okay, I will simply subtract the voltage ES1N between winding 1 and neutral and winding 2 and neutral, which is equal to minus 1.5 K ETR into sin omega t. ES2 S3 equal to ES2N minus ES3N equal to 1.5 K ETR into sin omega t. ES3 S1 equal to ES3N minus ES1N. So, these two will be in phase. So, this will be equal to 0, clear. So, these are the two different voltages we are getting. So, it will give the position of the synchro rotor, right. That means, transmitter rotor position can be predicted from this voltage, because we say that in all synchros we are getting the three different stator voltages. That stator voltage will indicate the position of the rotor of the synchro. It is to be noted that despite the similarity between the construction of the stator of a synchro and that of a 3-phase machine, only the single phase voltage is induced in the stator, okay, as if it looks that it is a single, 3-phase induction machine, very similar to the 3-phase induction machine, but you will see that a single phase voltage is induced in the stator. Now, what I did, I rotate the, previously you see this stator is in this alignment, is not it, straight away like this one, right. Previously what we had, I had the stator like this one, like this one, I had a stator like this one, clear. Now, I have rotated it by angle phi in anti-clockwise directions. I have rotated the stator in anti-clockwise direction by an angle phi with respect to S2. In fact, the positions which I have shown, that is considered to be the electric 0, right. You see there is angle phi, okay, which is making with the stator winding S2. If now the rotor is rotated to a position as shown in figure 2, okay, that is figure 2 I think, yes, the voltages in each stator winding will vary as a function of the cosine of the rotor displacement angle phi. The voltage magnitudes are ES1N K ETR cos phi minus 240 degree, okay, and this will be obviously multiplied by the sin omega t. Please note, because sin omega t will be there. So, I am not writing it everywhere, sin omega t is there because that is the excitation, is not, that signal will be always there. So, I am not writing into sin omega t K ETR cos phi minus 240 degree, ES2N equal to K ETR into cos phi, and ES3N, that means between the winding 3 and neutral, stator winding, stator between 3 and neutral, between 2 and neutral, between 1 and neutral. So, it is 1 and neutral KETR cos phi minus 240 degree, E that between 2 and neutral when the rotor is shifted by angle phi from the winding 2, okay, in anti-clockwise directions, KETR into cos phi, and ES3N equal to KETR into cos, sorry, KETN KETR cos phi minus 120 degree, clear, with sin omega t obviously that will be there. The magnitudes of the stator terminal voltage will be expressed as ES1 S2, okay, that means that in this position the voltages across the stators will be given by ES1N minus ES2N root 3 KETR sin phi plus 240 degree, ES2 S3 that means between the stator of the winding 2 and 3, between that is can be given by the voltage which will get at the stator 2 and neutral and the stator 3 and neutral, root 3 KETR sin phi plus 120 degree into sin omega t, everywhere sin omega t is there, and ES3 S1 equal to ES3N minus ES1N equal to root 3 KETR into sin phi, clear. You see, this is the plot of the stator voltages of a synchro transmitter versus phi. What is phi? Which is in counterclockwise directions. Plot of the stator voltage of this you see here, ES3 S1 which we have plotted like this, right, is not it ES31, okay. There is KETR into sin phi, sin omega is there, forget about that because we are drawing only with respect to phi. So, ES31 like this one, whereas S1 S2 you see S1 S2, S1 S2 has a, I mean 240 degree. So, it looks like this, you see at 240 degree it is becoming 0, whereas S1 S2 will like this one at 180 degree it will become 0, clear. Construction of a synchro. The physical construction of the transmitter and the control transformer are identical, except that the transmitter has a salient pole dumbbell shaped rotor while the transformer has a cylindrical rotor. This is the distinct difference or only difference between the rotors, because stator in the two cases are same, both in the case of transmitter and the control transformers. Only the difference is in the case of design of the stator, because to reduce the weight we have made dumbbell shaped, okay, whereas the control transformer rotor is the cylindrical shape. The construction is similar to that of a wound rotor induction motor, and figure 4 shows the coil arrangement of the transmitter rotor. See, this is the coil arrangement of the transmitter rotor and this is the control transformer rotor. There are two null positions of the rotor of the control transformer. This is a synchro rotors constructions. Okay. You see, this is dumbbell shape, whereas this is cylindrical shape. Why this is cylindrical shape? Dumbbell shapes already I have defined, and why it is cylindrical shape, that I will define after a few minutes. The rotation of the rotor changes the mutual inductance between the rotor coil and the stator coils. That is the reason I am getting different voltages, is not it? You see, I will read it again. Rotation of the rotor changes the mutual inductance between the rotor coil and the stator coils. For a given stator coil, the open circuit output voltage is sinusoidal in time and varies in amplitude with the rotor position, also sinusoidally as shown in the figure 3. Already we have shown that with changes of rotor positions, is not it? We have seen in the figure. Where is that figure? You see here, with the changes in rotor positions, okay, the signals vary sinusoidally, is not it? Okay. You see the signal varies sinusoidally with the changes in the rotor position. Rotation of the rotor changes the mutual inductance between the rotor coil and the stator coils. For a given stator coil, the open circuit output voltage is sinusoidal in time and varies in amplitude with the rotor position, also sinusoidally as shown in figure 3. Okay, because output voltage will be obviously sinusoidal, is not it? The 3 voltage signals from the stator coils uniquely define the angular position of the rotor. Okay. this will uniquely define the angular position of the rotor, in which position, whether it is clockwise, anti-clockwise, everything will be known from this. When these 3 voltages are applied to the stator coil, these 3 voltages will be applied to the stator coils of the control transformer. They produce a resultant magnetomotive force aligned in the same direction as that of the transmitter rotor. Okay. This will produce a magnetomotive force and which will align in same position, that means it will result in magnetomotive force aligned in the same direction as that of the transmitter rotor. The rotor of the transformer act as search coil in detecting the direction of the stator field. Rotor of the transformer acts as a search coil. That means, you see the rotor of the transformer can be act as a search coil. Okay. This will give you, because is there any mismatch between the rotor position of the two, of the rotor positions of the transmitter and the control transformers, I will get some output. If the axis of this coil is aligned with the field, the maximum voltage is induced into the transformer rotor coil. Okay. If the axis is perpendicular to the field, 0 voltage is induced and giving the null position mentioned above. Okay. The output voltage amplitude actually varies sinusoidally with the misalignment angle, but for small angle the sine and the angle are nearly equal, giving a linear output. Okay. How it is happened, let us see. The control transformer stator winding is similar to that of the transmitter, that is already we have discussed. The rotor of control transformer is cylindrically shaped to make the density of magnetic flux same at all positions of the rotor, otherwise the output voltage will be the function of the position of the control transformer rotor. So, that is very undesirable characteristic previously. Nowadays, you know, that is almost all the the output voltage should not be a function of that. So, we want to make the independent for that particular part. So, that is the reason the density of magnetic flux same at all position of the rotor, otherwise the output voltage will be the function of the position of the control transformer rotor itself. That I do not want, is not it. I want that the rotor output will be the mismatch of the position of the transmitter rotor to the control transformer rotor. But if the control transformer position of the control transformer gives additional change of voltage, that is undesirable, that I do not want. That is the reason the control transformer rotor is cylindrical shaped. So, that in all positions the same density of magnetic flux will be available. Okay. That is a distinct difference. Please note why it is done like this. This is done purposefully so that the output will be independent of the position. Only I will, if there is mismatch of the shaft positions of the rotor with that of the control transformer, I will get the output. But I do not want to get any change of output for the different positions of the control transformer rotor. That is the reason we made it cylindrical shape. I will read it again. Rotor of the control transformer is cylindrical shape to make the density of magnetic flux same at all positions. If it is same at all positions, what will happen in the case of rotor? In the transmitter. In the case of transmitter, because it is dumbbell shaped, if I change the position, there are different linkage, mutual inductance are different, so I am getting different sets of voltage. But here I will not get, in the control transformer I will not get that thing, right. That is the reason it is cylindrical shaped. Okay. Now, the voltage only differed, only what was the output voltage I will get from the stator of the control transformer, okay, that which will depend on the position or the position mismatch of the transmitter and the control transformer. Clear? Error detectors, that will more the function of an error detector is to convert the difference of two shaft positions into an electrical signals. Okay, that we want that if there is any mismatch of the function of error detector, if the mismatch of the difference of the shaft positions, I will get a electric signal. Therefore, a single synchro transmitter will not apparently inadequate, as I told you, single synchro transmitter will not occur. We always need a single transmitter. We need a transmitter along with a control transformer. That means we call it synchro pair. This is the, you see, we talked about. You see, stators are, look at very carefully, stators are connected. You see, all the stators corresponding, this stators is connected, this stators is connected to this stator is connected to this. I have a rotor, okay, and I have a single phase excitation here. Okay. Now, if these two rotors are in the same positions, I will get 0 output voltage. If these rotor positions are different, this position and these positions are different, I will get output voltage which can be given by E naught equal to sine of phi TR into phi CT. Is phi CT is the position of the control transformer, that is I am naming phi CT, whereas the phi TR is the position of the transmitter, that is the reason I have written phi TR. So, multiplying factor will be there K, that is I am not writing. This is the rotor output will pick up the voltage at this point R dash and R double dash, whereas I will take the voltage here, I will give the excitation is R dash and R double dash at there. This is the shaft of the synchro transmitter and this is the shaft of the synchro control transformer. Okay. What I do not want that for the different positions of the control transformer, I will get a different output voltage. This output voltage I will get, that will be only the mismatch of the two rotor, that means phi TR minus phi CT. But if it is not cylindrically made, this rotor of the control transformer is not cylindrically made, then what will happen, you see, for different positions I will get a different sets of voltage, even only for the. Now, if these two are same, phi TR and phi CT is same, I will get a 0 output voltage, because here at that position, because this output voltage will not change due to the position of the phi CT only, position of the rotor of the control transformer. This is the difference of the two transformer will give you output voltage. That is the reason this is dumbbell shaped and this is cylindrical shaped. Clear? Now, a synchro error detector is made of two synchros or a synchro pair, that is one transmitter and one control transformer. For small angular deviations between the rotor position, a proportional voltage is developed at the rotor terminals of the control transformer, right. That means, for small deviations you will find, we have seen that it is a sinusoidal voltage. So, for small deviations near the vicinity of the null, we can use it as a linear sensor, right. You see, this is a, you can see here. Okay. So, you can see for 15 degree almost we can see it is used as a linear sensor. The rotor voltage of the control transformer along with the versus error of the or mismatch or misalignment of the transmitter and the control transformer rotor, right. So, you see here it is voltage is increasing, it is coming like this one. So, near the vicinity of the null, okay, near the null I can say, sorry, so here near the vicinity of the null I can say it is a linear sensor. So, okay, during these positions I can say it is a linear sensor. So, for these positions I can say it is a linear sensor, okay. Otherwise, it is a nonlinear device. Obviously, sine is not a linear function, it is a nonlinear function. Synchro error detector is a nonlinear devices, but for small angular deviations up to 15 degree in the vicinity of the null position, the rotor voltages of control transformer is approximately proportional to the difference between the positions of the rotors of the transmitter and the control transformer. Synchro error detectors is a nonlinear devices, but for a small angular deviations of up to 15 degree in the vicinity of the null position, the rotor voltages of the control transformer is approximately proportional to the difference between the positions of the rotors of the transmitter and the control transformer. Mathematically, Ks equal to, we can write E equal to phi TR minus phi CT equal to E by, I mean phi E for small deviations. Okay, we are writing it because sin theta or equal to sin theta for small, is not it, that is we already know. That means sin theta is almost equal to theta when theta is small. Right, where E is the error voltage, phi TR is the shaft position of rotor of synchro transmitter in degree, phi CT, phi subscript CT, shaft position of the rotor of the control transformer in degree, phi E is the error in the shaft position in degree, and Ks is the sensitivity of the error detector, okay, is in volts per degree. For typical control transformer, the sensitivities lie between 100 to 500 millivolt per degree, and synchro accuracy is usually specified in terms the minutes of the error, as you know 60 minutes equal to 1 degree. A synchro having plus minus 10 minutes of accuracy will produce the correct stator voltages for a given angle with no more than plus minus 10 minutes of error signal. Apart from their use as a displacement transducer, such synchro pairs are commonly used to transmit angular displacement information over some distances, for instance to transmit gyro compass measurements in an aircraft to remote meters. Okay? That is also another use of this synchro transmitter. They are also used for load positioning, allowing a load connected to the control transformer rotor shaft to be controlled remotely by turning the transmitter rotor. Okay, by transmitting rotor, automatically whatever the given signals I have given or rotatory angles I have given to transmitter, that will be followed in the control transformer. You see, this is the, I mean, it's for low torque measurements. For low torque applications, we can use a synchro transmitter receiver pair. Okay, this is especially for the low torque measurements. You see, the rotor is connected to rotor and stators are connected to stators. So, what will happen, you see that whatever the rotations I will give to phi tier, whatever the rotations I will give to the phi tier, okay, same phi ct will rotate by the same angle. Whatever the rotations I will give in the phi tier, that the same angle will be given to the phi ct, right. So, there will be no error between phi tier and phi ct because those two rotors are connected together. I am giving a single phase supply here, I am giving a single phase supply here, single phase supply. Single phase supply I am giving here. Okay. So, this is basically it is a, I mean it can be previously you see this type of systems were used, suppose in a, I mean when the digital clock was not that commonly available some 30-40 years back, you can see that people are using this type of synchro, because in railway stations and all those places here, I mean airport previously, you know, all the watch should have the same time, and that time what they do, they have a master clock and they are connected through a synchro transmitter to a several slave clocks. And since all are connected together, because you know the rotations or the, it is basically low torque devices. I mean rotating the arm of the seconds arms or the minutes arms or the hour arms does not need large torque. Okay, so this is very well suited for this type of applications where a master clock, whatever way it is rotating, the slave will follow exactly the same. So, there will be no error or mismatch of timing between all the slave clocks, right. But basically as I told you, this is a low torque devices. For this application, the transformer rotor is free to rotate and is also dampened by preventing oscillatory motion. In the simplest arrangement, the common sinusoidal excitation voltage is applied to the both rotors. If the transmitter rotor is turned, this causes an imbalance in the magnetic flux patterns. Okay, the transmitter rotor turns, this causes an imbalance in the magnetic flux patterns and the results in a torque on the transformer rotor, which tends to bring it into the line with the transmitter rotor. The use of a synchro transmitter receiver pair is limited to relatively low torque loads, and overall accuracy is determined by the friction of the rotor of the control transformer and load bearings. Okay. If it is large, so it cannot be used, because that time we have to use some servo mechanism. Otherwise, for low torque devices, when the bearing problem is not that much, excuse me, I mean we can use this type of device, this type of, I mean connecting two rotors, shorting two rotors and shorting, I mean one stators are connected together. In all the pairs, I mean whenever you are using synchro pairs, all the stators will be connected at the like that, but if you use a servo mechanism, so we will not connect two rotors together, right. Excuse me. In ordinary applications such as driving an indicator pointer, as I told you, indicator might be the clock also, wall clock point at remote location, the receiver shaft will follow the transmitter shaft with less than 1 degree. This is highly accurate, you can see the 1 degree is nothing, right. So, in ordinary application such as driving an indicator pointer at a remote location, the receiver shaft will follow the transmitter shaft with less than 1 degree, clear. This torque is typically small and for small displacements, so that this technique is only useful if the load torque on the control transformer shaft is extremely small, otherwise you cannot, right. It is necessary to incorporate the synchro pair within a servo mechanism where the output voltage induced in the control transformer rotor winding is amplified and applied to the servo motor, which drives the transformer rotor shaft until it is aligned with the transmitter shaft. Okay. This we have shown, it is also spread up into two, these are synchro error detectors which I am going to show you. Single phase excitations, we have phi TR, we have phi CT, but it is spread over two slides because it is a big diagram, it cannot be accommodated on a single slide. Let us look at the next slide, you see here. Okay, previous slide, let us look at. Okay, this is now we have another, what we have? We have another. This goes to the next slide, please note, right. So, we have another, right. This will work as a error voltage. What is that? This is phi CT. So, in any mismatch of phi TR and phi CT will be get will be received as error voltage here. Okay. You see here, this is the things I just have done. Okay, this is our synchro control transformer rotor output, because this error voltage will be available in the control transformer rotor output. This rotor output is going to the amplifier, and this amplifier is fed to a two phase servo motor. Okay. And this two phase servo motor is there. So, this is another phase, and these two are in quadrature, right. So, the servo motors always will try to, with proper sign, to reduce this error voltage. So, it will reduce, it will rotate in a direction if you have a large load in a gear train. So, that the phi CT will automatically follow the phi TR until unless this error voltage becomes 0, right. We will see the details. This is our excuse me, block diagram of AC control systems. We have phi TR, this is our command, right. I want this particular positions, I am getting phi C. Our goal is phi CT should be exactly equal to phi TR. So, if there is mismatch, this is coming as a error. If there is no error, phi TR minus phi CT will be 0. If there is an error, there is a non-zero voltage will come down here. This will be amplified. This will go to the two phase servo motor. Servo motor will automatically make the correction until unless it rotate in a direction, until unless this error voltage becomes 0 and phi TR will be equal to phi CT. This is the block diagrams of our AC position control systems, right. Case is the sensitivity of the error detector and has opposite signs at two null position. Okay, it has opposite signs in two null position. In the closed loop systems, there exists only one true null position, and the other one corresponds to an unstable operating point of the system, right. Now, when the synchro positions are close to the true null, the rotor of the control transformer lags behind the rotor of the transmitter. A positive error voltage will cause the servo motor to turn in the proper direction to correct the lag. Okay. If this is positive, it will always correct the lag, right. When the synchro positions are close to the null, true null, the rotor of the control transformer lags behind the rotor of the transmitter, and a positive error voltage will cause the servo motor to turn in the proper direction to correct this lag. But if the synchro rotor is not in the true null position, then what will happen? Let us look at. If the synchros are operating close to the position which is not true null, for the same lag between phi TR and phi CT, the error voltage becomes negative. Okay? And the servo motor will rotate in the direction that will increase the lag. So, this will continue until unless we get the true null position. The larger the lag in the rotor position of the control transformer, higher will be the magnitude of the error voltage. Larger the lag, the rotor position control transformer, higher will be the magnitude of the error voltage, quite obviously, right. And it will cause the servo motor to rotate in the same direction until the true null position is reached. Until the true null position is reached, it will go like this one. Now, the synchro error signal can be properly written like this. If I take a blank page and if I take a blue, so it will look like this. It will be error signal. V t will be equal to, you can write k phi e t into sin omega t. Okay, I don't know. Let me erase. Okay, fine. Sin omega t. You can see this is a waveform of a modulated wave with a suppressed carrier, right. So, it is very similar to the modulated wave with a suppressed carrier, because sin omega t will be there always. So, it is which is a carrier wave and it is always will be there. So, error signal will be modulated wave with suppressed carrier, right. Now, we will discuss next, our topic is the microsync. Microsync is nothing but micro synchro. So, it is a trade name, I should say, some company has developed, and only features it has that it has no winding on the rotor. Since it has no windings, the tremendous advantage, there is no question of slip rings, right. So, obviously, there is a great advantage of this type of devices. This is also a position sensor, that means angle measurement is possible. Obviously, the load is less, okay. Torque is less, it can be used for the as a position sensors or for the angle measurements. Let us look at the details of this one. It is a rotary position sensor based on the variable reluctance, right. It is a variable reluctance sensor, right, based on the reluctance, as simple as that. This is our microsync. You see, this is diagrams of the microsyncs which I have shown. We have excitation voltage, excitation, you see these two coils are different. If you look at very carefully, you see this excitation is going through this one single winding, it is coming like this one, it is going like this, it is going like this, it is going like this. And the output voltage, these are also separate, there is no connection between this excitation coil and the output which we are tapping, right. You see this is going like this is going like this, going like this is going like this, going like this, is coming out, right. So, this is our output and we are giving the input excitation, single phase excitation voltage, clear. Now, you see these windings 1 and 3 we have done in such a way that this will aid each other. Now, winding 2 and 4 we have made in such a way also that winding 2 and 4, take a yellow pen, winding 1 and 3 will aid each other, 2 and 4 will aid each other, but will oppose 1 and 3. Now, in this position, in this particular position, so which I have shown, this is a rotor, this is basically made of iron, this is a rotor, this is a null position. Why it is null position? You see, in this particular position, the reluctance of the coil between 1 and 3 or between this and this, okay, between the iron and the coil, okay, and between iron the coil number 3 will be exactly balanced by the reluctance, because if the reluctance is large, obviously the inductance will be small. What will happen? You see here the reluctance of this between soft iron, this iron and the coil 2 and the iron and the coil 4 will cancel each other, we will get 0 voltage. If it moves, I will get an unbalanced voltage, right. That is the typical beauty of this synchro, this microsync. There is, you can see here, there is no winding on the rotor of the, I have taken a section, there is no winding on the rotor of this microsync, right. As shown in figure 10, the rotor is connected to the input shaft. When the input shaft is in the null position, where the voltage induced in coils 1 and 3 which aid each other are just balanced by those of the coils 2 and 4, which also aid each other, but opposes 1 and 3, right. This is a balance condition. That means as I told you, the voltage induced in the coils 1 and 3, which aid each other, will be exactly balanced by those of the coils 2 and 4, which aid each other, but opposite to the coils 1 and 3, that I told you at the beginning of this microsync, right. Now, if now the shaft rotates in clockwise direction, then what will happen? If the shaft rotates in the clockwise direction, okay, from the null position, reluctance of the coils 1 and 3 increases. Let us go back, you see here, if it rotates in this direction, then what will happen? Reluctance between coil and 1 and 3 will increase, because reluctance also depends on this iron. So, reluctance between 1 and 3 will increase, and reluctance between coil 2 and 4 will decrease. I will get unbalanced voltage. That unbalanced voltage will tell the position of this rotor, okay, or the angle measurements will be over. If now the shaft rotates in a clockwise direction, as shown in figure 10, from the null position, reluctance of the coils 1 and 3 increases and reluctance of the coil 2 and 4 decreases. What will happen in result? As a consequence, induced voltage in coils 1 and 3 decreases, because we have a large reluctance, induced voltage will decrease, and that of the coils 2 and 4 increases, because the reluctance has decreases. So, I will get a large unbalanced voltage. Therefore, a net output voltage E naught will be available from the microsync. Okay. So, I will get excitations, I will get an output voltage, the output voltage will tell you the position of the rotor. Now, if the shaft moves in opposite direction, okay, microsync gives an output voltage, but with a 180 degree phase shift, right. So, it is very difficult in both directions, whether it is clockwise direction or anti-clockwise directions, I will get a same unbalanced voltage. But if I want to sense whether the rotor has moved in the clockwise directions or anti-clockwise directions, I have to make some phase sensitive demodulations. Okay, that is why I am telling. Now, if the shaft moves in opposite direction, microsync gives an output voltage of the same amplitude with 180 degree phase shift. That means, if the position is same as in the clockwise direction, if the anti-clockwise direction position is, the amplitude of the signal will remain same, but with a 180 degree phase shift, right. The phase sensitive demodulations of the output voltage is necessary if a direction sensitive output is required. If the direction sensitive output is required, then a phase sensitive demodulation will be necessary here, right. Output is required. Now, specifications let us look at. Excitation voltage is 5 to 50 volt. Okay. Then we have this is a typical excitation voltage. That's we have excitations, we have an output, already we have discussed. An excitation frequency, it lies between 50 hertz to 5 kilohertz. A typical range depends on the size and all those things. We can use this up to 50 hertz to 5 kilohertz. Then sensitivity 0.2 to 5 volt per degree. You can see the sensitivity is enough to get the signals. Okay, that's I don't need further amplifications. Whatever I will get from the microsync, the signal is enoughly high. I mean, it is enough high so that I can use directly that signal to make my angle measurement. Or obviously, it is an AC signal. It is not very difficult. I mean, to amplify the signal if the signal is even small. Suppose if it is 0.2 volt, that means 200 millivolt. It is not very. We can get an amplifier. Simple single amplifier devices can amplify that signals. Okay, and I can get a large resolutions of the, I mean, I can measure a smaller angular. I mean, it is not that we will measure a fraction of that, I mean, degree, but you can do it. We can have a large output voltage. Obviously, the sensitivity is quite high. Nonlinearity is 0.5% of full scale for plus minus 7 degree of rotation. Okay. So, plus minus 7 degree of rotation is 0.5% of the full scale readings I will get. Okay. And 1% of full scale for 10 degree of rotation, because it is a nonlinear devices, it is a reluctance based. Already we have seen that the two coils will be there. So, obviously, you will get is a nonlinear device, because it basically principle depends on as well same as synchro. Only difference is that there is no winding on the rotor, otherwise it is same. So, I will get a sinusoidal signal again. Okay, I will giving a sinusoidal signal, so obviously it will be a now null voltage, because though I am saying that the you see that the voltage 1 and 3 will exactly cancels. Okay, what is that? Okay, I am saying in the micro scene that is a soft iron core, no winding, nothing to the core. So, the reluctance when it in this position, reluctance between this and this, okay, and reluctance between this and this will aid each other, this will also aid each other, but it will oppose. So, it will exactly same. So, I will get a 0 output voltage, clear. But what will happen, it moves, then I will get a non-zero output voltage. So, non-zero output voltage, why it is simple that between 1 and 3 what will happen, if it moves, the reluctance between 1 and, because this moves, this iron ore has moved, this core has moved. So, reluctance between 1 and 3 will increase and reluctance between these 2 and 4 will decrease. But though I am saying that at these positions we have exactly the these two voltages, that means when it will in this position reluctance will between this and these two coils with this position of the core, and reluctance between these two coils is exactly same, though it is in the figure it appears to be exactly same, but two windings, the two magnetic circuits is very extremely difficult to make exactly identical. So, there will be always some mismatch. So, though it is a null position, that means these two voltages and these two voltages will nullify each other, but you will get a non-zero voltage, right. That is actually I want to that is to be specified, that is called the null voltage of a micro scene, right. Null voltage is less than the output signal generated by, so it is 0.01 degree of rotation. Obviously, it is quite small, as you can see, that is actually we are not interested in measurement of such a small angle, but it is less than the output signal generated by the 0.01 degree of rotation. It is extremely small, okay, this null volt. That means, this voltage will be equivalent to a voltage which is will get from the micro scene when it is rotated by 0.01 degree, clear. Advantages, as I told you earlier, this micro scene has advantage over the synchro, conventional synchro, but the application areas is very narrow, as I told you. I mean, compared to synchro, it is nothing. And very small angular displacement can be measured, because there is no slip rings, because slip rings will make a nuisance. It will always allow you to make the problem, that is it will use additional resistance to the rotary systems. So, that smaller angular measurements are extremely difficult. Very small angular displacements can be measured with this type of systems, right. And no slip rings are required for the rotor excitation, in contrast with the synchro. That is the great advantage of these particular devices, but especially as I told you, it is a very low torque devices compared to synchro. It is not that popular, just some manufacturer company we have used. Only advantage that is prominent, these are the two prominent advantage what you have in the micro scene or micro synchro, right. With this, I come to the end of the lesson 30 of industrial instrumentation. Welcome to the lesson 31 of industrial instrumentation. In this lesson and the subsequent lesson, that means lesson 31 and 32, we will discuss basically the dissolved oxygen sensors. Dissolved oxygen sensors was not that important, some time back, but due to the evolutions of the biotechnology in a very big way. So, this is to be considered very thoroughly, and also it has a tremendous application, because the newer the bioreactors are coming up in the markets, and lots of new product are coming, like medicines, then antibody, which is basically the growth of cells. So, and in these particular situations, we must consider the dissolved oxygen sensor. That is one of the only sensors which can measure the dissolved oxygen concentration rather than the partial pressure of the oxygen in a liquid medium, and this will give you a lot of other informations which is not exactly measurable, which usually we have to estimate. So, that is the reason this is also this these dissolved oxygen sensors we brought under the industrial instrumentations. and it has also, I mean I should say that it is also used as a, I mean, measurements of the dissolved oxygens in environments like the water treatment plants and the water discharged where it is in the, I mean, because there is some safety level of the water, I mean dissolved oxygen concentration, which is essential for the living animals like fish and others, algae and all those things. The current output of the electrode is proportional to the oxygen flux at the cathode surface. Now, NFA PM will be equal to multiplied by partial derivative of P with respect to x at x equal to 0, that means at the cathode surface, where NFA and PM are the number of electrons per mole of the oxygen reduced, and Faraday's constant, which is F is the Faraday's constant, is the surface area of the cathode, which is very easy to calculate because it is a pi r square or pi d square by 4, and the oxygen permeability PM is the oxygen permeability of the membrane respectively, right. Okay. N is the number of electrons per mole of oxygen reduced, A is the Faraday's constant, A is the surface area of the electrode cathode, and PM is the oxygen permeability of the membrane respectively. The permeability PM is related to the diffusivity of the oxygen by the following expression. What is that expression? PM equal to dm into Sm. What is Sm? Let us look at, where Sm is the oxygen solubility of the membrane, and from equation 5 and 6 the current output IT, current output, because actually that is the only measurement, that is the reason we are going for the membrane based electrode, membrane covered electrode, otherwise we can make the chemical analysis. We need this current output for continuous measurements or continuous control of the partial pressure of oxygen or dissolved oxygen concentration either in the bioreactors or in the wastewater treatment plant. As function of time will be expressed as follows. This is equal to, you see, the current output IT equal to N F A PM by Tm multiplied by PO 1 plus 2 summation n equal to 1 to infinity minus 1 to the power n exponential minus n square pi square dm t upon Tm square. This is equation number 8 in IIT Kharagpur in the bioprocess instrumentation lab, and we found that we got a consistently good results, though the result inconsistent obviously, but when we measure with the other sensors, so there is a slight offset that which is quite obvious. So this galvanic electrode actually it worked very nice in our laboratory, right. So with this I come to the end of lesson 31 of industrial instrumentations. Basically we have considered the dissolved oxygen sensing here, and basic more details of the sensor, 4 different more details of the sensing will come in the lesson number 32.